Welcome back. This is part 2 of the Gram-Schmidt procedure. So we're in the process of computing U sub 2, and we had calculated the inner products. We had calculated the ratio of the inner products, and that's what we're calling alpha as a scalar. And then we had expressed alpha 1 times u1 as a whole vector, a vector on its own. So what is next to follow up with this calculation is to compute this subtraction, the fixed vector v2 and the subtraction. You can think of this as an addition of vectors, right? So we want to put those two vectors in the same place and carry out the calculations. So that means that v2 minus alpha 1 u1 is going to take this form, right? We had already computed that scalar vector product, and that's going to be the vector that appears second in this subtraction. The first vector is v2, and that vector is no other than minus I 1 and 1 plus I, right? So what we do next is that we carry out these calculations. For that, probably is convenient to write these expressions here in terms of fractions. And in doing so, well, there's some fraction arithmetic here that you arithmetic and rational numbers and adding and so on. And so after you do some of those calculations, these are things that require a lot of as I said, you have to be a very good bookkeeper, okay? And you really like to have two pieces of paper when doing this. The one in which you're doing the original calculation, then on the side, you have to do many of these manipulations with fractions. So after you do that, then you'll find out that this subtraction between these two vectors reduces or becomes this vector that has these entries, the second of which is 1/4 minus 1/4 times I, and the last entry here is 2/4 plus 5/4 times I. Okay, so this is exactly what we will call U sub 2. So this is the second in the construction of this new set of vectors, and we're doing this construction, we're building these vectors based on this algorithm called Gram-Schmidt. So what goes next is to construct the vector U3. So that vector U sub 2 in a very compact and clean way after some manipulation, that vector can be expressed as with a common factor in front of it, right? So you can pull 1/4 or a common factor is scalar. This is kind of thinking of this scalar 1/4 multiplying this column vector, right? So you can write 1/4 as a scalar in front as a coefficient, and so then that makes the entries look in each of those entries is now an integer, not a rational number. Okay, but this is what u2, either in this form or in the previous one, this is what the vector, the second vector, looks like. So the formula of Gram-Schmidt has this general form. We are right now at value of k equals 3, which means that k minus 1 is 2. Okay, so that gives us an indication at which term of this whole expression we are going to stop, right? So, and precisely the last term, so here u sub k minus 1 would be u sub 2, and that means that this is the last term in that expression. So we have, we're going to have u3 equals v3 minus this coefficient multiplying u1 minus that coefficient multiplying u2. So here's where we want to think of these terms as scalars. So I'm going to call this b1 and I'm going to call this b2. So we're really thinking here of looking at this as v3 minus b1 u1 minus b2 u2, and that's what we need to compute in order to obtain u sub 3. So now we, to compute scalars b1, b2, first for b1, we require the calculation of this inner product between u1 and v3. So we have an expression that looks like this, and then for v3 here we enter 0, and then I, and so that means this calculation is looking like 1 minus I plus I, and excuse me, this this is not correct. When in fact, let me just redo this. Okay, we need to multiply this I times I and I times 1. So in doing so, we obtain I minus I squared plus I squared is -1, so this is going to be 1 here up front, and then this becomes 2I. So this inner product equals 1 plus 2I. The other quantity we need to compute is the inner product of U1 times itself. We had previously computed that this equals 4. So that means that B1 is going to be equal to the ratio of these two inner products. Okay, this is U1 V3, and then U1 times itself. Okay, and so this would be 1 plus 2I divided by 4, which gives us 1/4 plus 2/4 times I. So the following inner product is a little more elaborate, right? So we're writing here the expressions for the conjugate of U2, and each of those multiplies entries of V3. And so the first um, entry of V3 is 0. The next one is I, and the last entry is I2. So this whole term is going to go to 0. So that means that we're distributing here. So this is 1/4 times I plus 1/4 times I square plus 2/4 times I minus 5/4 times I square, right? And so we can see that these I square terms, this becomes -1, this becomes positive, this is -1/4, this is positive 5/4. So we have 4/4 plus 1/4 I plus 2/4 I. So this would be 3/4 times I, right? So um, this is what this inner product U2 and V3 is equal to, and the other quantity we need to compute is the inner product of U2 with itself. So in doing so, we end up with inner product of U2 and U2 gives means that, remember, this is also equal, this expression is also equal to the square of the norm of this vector U sub 2, right? So that's equal to that expression, and it turns out that this is giving us 4 plus, there'll be a lot of numbers there. The denominators is 16 for all of them. So 4 plus 9 plus 1 plus 1 plus 4 plus 25. So this number here is going to end up being equal to 44 over 16, right? So the square of the norm of U2, or the inner product of U2 and U2, equals this number 44 over 16. So this means that the scalar B2, which is the ratio of the inner products U2 V3 over square of the norm of U sub 2, this is an expression equal to we can write this expression as 1 plus 3/4 times I in the numerator, and in the denominator we have 44 over 16. And after doing some simplification, then we find that B2 equals 16 over 44 plus 3 over 11 times I. Okay. So what we would need to do is to put that all together, right? So what um, we know is that this is going to be the expression we want is U3, and we want to think of this first term as B1, this other ratio as B2. So we're really looking at this as V3 minus B1 U1 minus B2 U2, right? And the structure of this is something that looks like here's vector V3, and then we have an expression for B1, and here's the vector U1. And so very important here is to remember, keep track of your calculations. Be very meticulous about your calculations. So probably what you want to do next is to compute this scalar vector multiplication. So basically this term here, which involves multiplying B1 times U1, do that as a separate calculation, and then carry out the calculation B2U2, which is precisely what you have over here. So once you do that, you're going to end up with one vector, and then it will be easy, well, or more manageable to write vector minus vector minus vector. And at that stage, it becomes really an addition of three vectors, and then you will end up with a vector that has this form here. So in summary, we have used the Gram-Schmidt procedure to construct vectors u1, u2, and u3, which have this shape, and this, because of this Gram-Schmidt procedure, we would find that this set is orthogonal. So this is another thing that you can verify. You can compute now the inner product of u1 and u2, and then the inner product of u1 and u3, and also the inner product of u2 and u3. And what you will find is that by construction, these inner products are equal to 0. Okay, because that's precisely the idea that this vector is an orthogonal, this set of vectors is an orthogonal set. And by the theorem we saw initially, that fact also implies that there is linear independence on this newly constructed set.